Intermolecular forces effect on bulk properties. The goal for this video is going to be to define how intermolecular forces affect boiling and melting point. We'll then want to be able to rank given compounds in order of boiling or melting point, and explain boiling and melting point's orders of more complex molecules. So these will be examples where maybe this doesn't follow the exact rules I talk about here, but you should be able to explain why that might be the case if I give you the answers. So first, we need to do a little bit of a reminder on what happens when something boils and melts so that we can talk about why intermolecular forces would matter here. And then if we increase the strength of the forces between the molecules, how is that going to change the boiling and melting temperatures? So first, let's talk about boiling and melting. So if you have something that is going to be boiling, you have everything kind of rummaging around. There's in close contact, it's touching each other, but it's not in a solid crystal. And then when you apply some heat to this system, it gives everything enough energy, and so a little bit at a time, the molecules are able to escape the liquid and go boiling off. And how much heat you need to add to that is dependent on how much these are going to stick together. Melting is kind of a similar situation, where we have our solid crystal structure, and then as you apply some heat to it, it starts to come away from, it breaks the bonds of that solid crystal structure and becomes more of a liquid, and then it starts to be able to move around on top of each other rather than being in this solid lattice. So now, given both of these situations, they're very similar. It's adding in heat, adding in energy in order to give atoms or molecules enough energy to break these forces either between the crystal or between the liquid. So if we were to increase the strength of the forces between molecules, what's going to happen? If we take this liquid substance and now we replace it with a different one where all of these are held together by much stronger forces, well then what are you going to have to do to make it boil? If it's held together tighter, you would need to increase the amount of heat that you put in order to let it boil. The same thing with the melting. If we were to replace this with some other atom or molecule that held each other much closer, that grabbed onto each other with much stronger, that had higher intermolecular forces, then we're going to have to put in more heat in order to break this crystal structure and let it become a liquid. So if you increase the strength of the forces between molecules, you increase the boiling and the melting temperature. Now here I have a graph from one of the textbooks, and we can see this happening if we look at this. So let's first look at this bottom group. So here we have CH4, SiH4, GeH4, and SnH4. So if you look at these on the periodic table, you can see it's just going down the periodic table. Now, as you go down the periodic table, what happens to the amount of electrons that you're working with? It increases. So if the amount of electrons that you have increases, that changes your dispersion forces. And so the lower down the periodic table you go, the higher your dispersion forces, the higher your intermolecular forces, and so your boiling point increases. Now, for right now, let's just stay on these 3 points in this area. Now the same thing happens if we look at the next rows over. So we have phosphorus with 3 hydrogens, hydrogen, bromide, and HCl, HBr, and HI. And you'll see that these 2 increase. Here we have pH3, ASH3, and SPH3. And as you add more electrons, you get more dispersion forces, and so it increases. And same thing here, sulfur, selenium. As you increase, you get more dispersion forces, and your boiling point increases. Now let's look at what's going on right here. Why is there a drop here? Even though we have more dispersion forces, there's a giant drop in boiling point. Well, what does water have that H2S doesn't? And what does HF have that HCl doesn't have? What does NH3 have that pH3 doesn't have? You said hydrogen bonding, you're correct. So since these have hydrogen bonding, they have much, much stronger intermolecular forces. And so these have the highest boiling points of all in the group. Then you drop down because you're dealing with this, and you increase slowly as you increase your dispersion forces. Now let's work through some examples so that you can see how this actually can be used. So Let's start with ranking examples where I'm going to give you some compounds and we'll work through and rank them in order of boiling or melting point. It doesn't actually matter which since the trends are the same. So here I have our noble gases listed out, and I want to rank those in order of increasing, let's say boiling point in this case, since they are noble gases. Okay, so our first decision here is which ones have the most/least intermolecular forces. Now, if you have lots of intermolecular forces, you'll have a higher boiling point. If you have less intermolecular forces, you'll have a lower boiling point. So here, since we don't have any dipole-dipole or any hydrogen bonding, all we're looking at is dispersion forces. And the more electrons you have, the more dispersion forces you have. And so the order here will be the same as the order on the periodic table, with helium going up to xenon because heliums have the least amount of electrons while xenon have the most. Now let's do another one. Here we have pH3, CH4, and H2O. So we have to decide why each one of these would be in the order that it is. So for this one, it may be helpful if you need to draw the Lewis structures, especially for pH3. So you may want to pause and take a moment to do that. All right. So let's start by actually picking the one that's going to be the highest because I think we can pick that one out first. So here we only have one molecule that has hydrogen bonding, and we know that hydrogen bonding makes a huge difference in melting and boiling point. So which one here would be our highest? Hopefully you said water. So water will be our highest. Now we have to look at CH4 and pH3. Now there are two things that may draw you toward one over the other. So first of all, pH3 is going to be larger than CH4 in the sense of electrons. There's more electrons, so it's going to have more dispersion forces. And there's one other thing that you may or may not be thinking about here. We've talked about carbons and hydrogens not being very polar. Carbon-hydrogen bonds not being very polar. And so you know that one isn't polar. Now, what about pH3? Now, this is one of those interesting topics where it's actually a little bit more complex than you would think, and so I wouldn't ask you it on an exam. However, on a homework question, we can look up the dipole of these. And oddly enough, because of the way that the geometry works, it does turn out that pH3 has a very small dipole. So the two reasons for the CH4 pH3 ordering here is that one, we have more dispersion forces because there's more electrons, and also that pH3 has a little bit of a dipole. Don't worry about why that is. If I were to ask you this on an exam, I would definitely tell you that there was a dipole or give you some numbers about there being a dipole and ask you to explain. So those are the two reasons for this. Let's do one more. Okay, so we have this set up. Now, there's a couple of things we want to start noticing here. Which ones have hydrogen bonding? So we know that this one has hydrogen bonding and this one has hydrogen bonding. Even though this has a hydrogen and it also has a fluorine, no hydrogen bonding is going to happen here because all of these hydrogens are bound to the carbon. So this one has dipole-dipole forces, but no hydrogen bonding. So we'll look at this in a bit more detail in the next slide. But I did mention it when we talked about hydrogen bonding, that the more donors and acceptors you have, the higher the intermolecular forces are. So here we have only dipole and dispersion forces. Here we have dispersion forces, dipole, and hydrogen bonding with just one donor acceptor. And here we have two donor and acceptor hydrogen bonding. So we'll order it in terms of no hydrogen bonding, one hydrogen bond donor and acceptor, two hydrogen bond donors and acceptors. Let's do a couple more examples. This time where I ask you to explain some things for me as opposed to just ranking. So here I tell you that C2H5OH has a higher boiling point than butane. Now, why would that be? Well, this has hydrogen bonding, and this only has dispersion forces. So even though butane's heavier, has more electrons, even though it has more polarizability, this has hydrogen bonding, and so this has the higher intermolecular forces, and therefore the higher boiling point. Now, water has a higher boiling point than H2TE. This will be a very similar explanation. H2TE doesn't have as much of a dipole and doesn't have hydrogen bonding. So because of the hydrogen bonding combined with the extra dipole-dipole forces, this water is going to have the much higher boiling point. Now, a little bit more complicated one. Acetic acid has a lower boiling point than benzoic acid, but they are very, very similar. So I want you to explain that. So first of all, what makes it so that acetic acid would have the lower boiling point? We can see that they both have this OH. They both have this carboxylic acid group that gives it a dipole. But this one is going to have more of a dipole than this one because it's much smaller, so it makes a much larger difference. But this one has this giant benzene ring structure right here, which gives it a lot of polarizability. So acetic acid has a lower boiling point because benzoic acid has more polarizability because of this benzene ring. Now, however, they're going to be relatively similar because even though acetic acid is much smaller than benzoic acid, this giant carboxylic acid group compared to this very small CH3 group gives it a much larger dipole than benzoic acid. And so they actually end up canceling each other out a little bit, and they are very similar. So a reminder then on your strengths. So we've covered this already, but now you have some examples to pull from it. Your hydrogen bond is your strongest in general, and the more hydrogen bond donors and acceptors you have, the stronger it is. Dipole-dipole comes next. Molecules with a dipole are in general going to have a stronger intermolecular forces and higher boiling and melting points than those with just dispersion forces, although of course there are exceptions. And then dispersion forces are your weakest. So here I can go into a bit more detail on what I was discussing with the hydrogen bonds and having more hydrogen bonds donors and acceptors. So let's start here with water. We're used to talking about water having a pretty high boiling point, and that's because of its hydrogen bonding. Its hydrogen bonding makes it so that it can interact strongly with other molecules, and then it holds itself together quite easily. But if we look at something like what we have here, where now we have our 3 carbons, we have an OH group and an OH group, we've added an extra oxygen here. And so this allows even more hydrogen bond donors and acceptors, and even more hydrogen bond to happen. Because now this part of the molecule can hydrogen bond, and this part can hydrogen bond. Now you have the added issue of it being much larger, and so you have much more electrons, and so you also have more dispersion forces as well. Now, moving up to here, we see another giant jump. Now, once again, we have added some electrons, so we have a little bit more dispersion forces, but the main jump here comes from the fact that here we had 2 OH groups, here we have 3 OH groups. And so this is very, very viscous and a very, very high boiling point, all because of how many hydrogen bond donors and acceptors we have. So now that we've done this video, you can take what we learned from the previous video with the intermolecular forces and see how those affect the boiling and melting point. This allows you to rank given compounds in order of boiling and melting points, as well as for more complex examples, explain what I tell you about the boiling and melting points.